Okay, welcome to the practice pulley problem that I'm going to post. I'll give you a second to draw this picture here. I have made a beautiful drawing of a ramp with two masses on it connected by a pulley. Mass 1 is 10 kilograms and mass 2 is 9 kilograms. And we have to determine which way this system is going to go. Now, the ramp is at an angle of 40 degrees. Let me include that degree sign in there. And the coefficient between block 1 here and the ramp, mu, is 0.2. So we need to determine what our acceleration is going to be. And just by looking at this, we have to be aware and kind of see ahead of time what we think might happen, because mass 1 and mass 2 are very close in size to each other. So I'm expecting a pretty small acceleration, or maybe no acceleration at all, because there's some coefficient of friction here. So this might be stationary. So our first step, as always, we want to draw a beautiful picture. So hopefully by the time I'm done with all of this talking, you will have drawn a beautiful picture in here. So let's look at mass 2 first. So the forces on mass 2, we have gravity, which wants to pull it down. So let's draw that in there. I'm going to label it M2G. And I have tension from this string right here. And I'll put that in green with some green T. And we'll call that tension. And are there any other forces acting in on mass 2? Very good. There aren't any other forces. That was a nice pause I had there. So we can look at the forces now on mass 1, connected by a string, so there's going to be tension as well, but in the opposite direction. I'll label it T. And I got gravity acting on this guy. We'll put gravity, we had purple over there, so we'll do purple again over here. So gravity points straight down, like always, and I'll label this M1G. And now gravity's going to have components for us. There's this component that is perpendicular to the plane, and this component that is parallel to the plane. The perpendicular component is going to be M1G cosine theta, and the parallel component will be M1G sine theta, because this is our angle right in there. That's our theta. That represents the angle of our ramp. And now we have the normal force acting on this block, because this block isn't crushing through the ramp or flying off of it. That just makes no conceptual sense. So force normal. And I also have the force of friction in here. And friction will always point opposite our direction of motion, but I'm not sure yet which way my direction of motion is going to go. So I first need to determine that. So if mass 1 was all by its lonesome, what would it want to do? Yeah, it would want to go down the ramp. And what makes it want to go down the ramp? Now you will answer gravity, and I will say yes, specifically what component of gravity, and you will tell me mg sine theta. So mg sine theta makes mass 1 want to go down the ramp. And now let's look at mass 2. So if mass 2 was all by itself, what would it want to do? Correct, it would want to fall straight down. And what makes it want to fall straight down? Gravity. So the force here is going to be M2G. Now we need to determine which of these forces is larger. So whatever force ends up being larger, that's the way our system is going to go. So we plug in our numbers. Mass 1 is 10 kilograms times gravity times the sine of 40. So if we plug that in, 10 times 9.81 times the sine of 40, I get M1G sine theta is equal to a force of around 63 newtons. And now we do M2G. So M2 is 9 kilograms times 9.81. Okay, so that's like 80 something. And I can see that M2G is the larger force. So that means our system is going to go around our pulley that way. And that means because friction opposes us, our force of friction will point down the ramp. And the final step, we need to put in a coordinate system. And we always put in our coordinate system so that our x direction is in the positive direction of motion. So I will draw that in right here, that this is our positive x direction, and that's our positive y. So anything that moves up the ramp, anything that points up the ramp is positive for us. And if we follow our pulley around, because our pulley just changes our direction, anything that goes down like this, except you can't see my hand right now. So I'll actually draw that in. So anything that goes in this direction following this black mark is in the positive direction. So anything that goes down is going to be positive. Alright? So we've drawn our beautiful picture. We've figured out which way it wants to go. So now we're going to do our sum of the forces. So let's do mass 2 first, because there aren't a lot of forces acting on it. So I'm going to title it mass 2 up here, so we know what we're talking about. So sum of forces in the x direction on M2AX. So at the A acceleration is our acceleration in direction of motion. So this sum of the forces in the x direction, it just means, hey, look at our beautiful picture, and we're going to add up all of our forces that act in the x direction, and all of those forces, all of the forces cause the mass to accelerate. So I need to take into account all of my forces that are acting on mass 2. Looking at my picture, what forces do I have acting on mass 2? Gravity, yes. Specifically, mass 2 times gravity. Now, is that positive or negative? Well, if we follow our coordinate system around, M2G points down, so that's going to be positive for us. So M2G is positive, so that's one of our forces. And the other force acting over here, I have tension. And tension points back up. That's in the opposite direction of what we have called positive, so tension is negative. So minus tension equals M2AX. Those are all of my forces causing my mass to accelerate. Now, we've gotten probably pretty good at this, so we know we're probably going to want to get this tension all by itself. So to do that, I'm going to subtract the tension over to that side and move my M2AX over so that I have M2G minus M2AX equals my tension. Okay, and that's all we can do for the mass 2. So we're going to take a gander over at mass 1. And let's look at the sum of the forces in the y direction for mass 1. So anything that points in this plane right here. So let's write this out. The sum of the forces in the y direction equals M1AY. Now looking at this AY, is this block accelerating in the y direction? Is it flying off of the ramp or sinking down through it? No, it's not. So I know that whatever forces I have adding together, they are going to equal 0. So the forces that I have acting here are force normal, which points in the positive direction, and mg cosine theta, which points in the negative direction, or negative y direction. So I have force normal minus mg cos theta equals 0, and then so bringing mg cos theta over to the other side, I have force normal equals mg cosine theta. And that has to be the case that these two forces are equal to each other, this guy here and this one here, because our block isn't flying off the plane. And the only way that can happen is if those two forces are equal to each other. So at this point, I know I often have force normal in my force of friction, and by often I mean all the time, because the formula for the force of friction, Pfuffen, equals mu times force normal. And this is an equation that you will be given, but I like to put it down here because I know, hey, there's a force normal here, force normal here. I'm just going to plug that in right here. So I will have that the force of friction is equal to mu m1g cosine of theta. I guess I should put the 1 over here just to make sure that we're keeping everything straight. So the force of friction is equal to mu m1g cosine theta. And I know I'm going to need that later on because looking at my picture, hey, there's a force of friction over here. So that will need to be accounted for. Okay, so the last sum of the forces, I'm still talking about mass 1. This is still mass 1. I need to do the sum of the forces in the x direction for m1ax. So this, we know this block should be accelerating in this ax direction, so we're not going to be able to cancel that out. So I need to add up all of my forces, add all of the forces up, acting on mass 1 in the x direction. So going back to look at my picture, let's see what forces I have. I have tension, and that's positive because it points in the positive direction here that we have defined. And I have the force of friction, and that's negative because it's fighting us. It's in our opposite direction of motion. It points down the ramp. And the last one, I have m1g sine theta, and that fights us as well. That points back down the ramp. This block wants to go down the ramp. So let's get to it. I have tension minus the force of friction minus m1g sine theta equals m1ax. Alright, but now again, I don't know tension and I don't know ax. But back on this previous slide, hey, we figured out what tension is equal to. So what we're going to do is do our substitution and take this equation and plug it in right over here for my tension. So this is a positive tension over here. So this m2g minus m2ax equals T. This part will go in right here. So this will look like m2g minus m2ax minus my force of friction minus m1g sine theta equals m1ax. Sweet. Now I only have one unknown because I know m2g, I don't know ax. I know my force of friction because I've solved for that over there. And I know m1g sine theta, I don't know ax. So I only have one unknown in one equation. So I need to get all of those guys by themselves. So I'm going to subtract or add m2ax over to the other side. And I'll continue writing this on the next slide. So I will have m2g minus the force of friction minus m1g sine theta equals m1ax plus m2ax. Now I'm like, hey, I got an ax in both parts here, so I'm going to factor out an ax, m1 plus m2, and then to get ax by itself, I will divide by m1 plus m2, and so this side gets divided by m1 plus m2. So now I have m2g minus the force of friction minus m1g sine theta divided by m1 plus m2 equals ax. And I'll continue writing it on the next slide because I need to plug in for what this force of friction is equal to. But lucky for us, we already know that right there. It's equal to mu m1g cosine theta. So plugging this in on the next slide, change color, it's fun. m2g minus mu m1g cosine theta minus m1g sine theta, all divided by m1 plus m2 equals ax. There it is, our final equation, and I know all of these things, so it's just a matter of plugging them in, and let's do that. So this is going to be 10, or m2 was 9 kilograms, so 9 times 9.81, I get 88.29 newtons for this section right here. So 88.29 newtons minus, so mu is 0.2, so 0.2 times 10 kilograms times 9.81 times the cosine of 40 is 15.03 newtons. And then minus m1g sine theta. So 10 times 9.81 times the sine of 40 equals 63.06 newtons divided by m1 plus m2, 9 plus 10, plugging that into my calculator because we certainly need to do that, is 19 kilograms equals ax. Alright, so this part right here represents mass 2, the mass that's causing our motion. This is our friction fighting us, and this is what mass 1 wants to do. And all of these forces get divided by the total mass to give me my acceleration. So 88.29 minus 15.03 minus 63.06, I get 10.2, and then that gets divided by 19. I get an acceleration of 0.537. I get that ax equals 0.537 meters per second squared. Okay, so this is a positive value, so I know this is actually moving, because if I had gotten a negative value, we would have known, because we checked our coordinate system in the very first step, we would realize that, hey, that negative value means that my system is not moving. So here is a case where even though M1 is larger than M2, the system is still going around towards the smaller mass. And that happens because of the ramp there. So a quick way, if you want to see our shortcut method, is where we take into account all of our forces acting in the x direction. All forces in our direction of motion. In direction of motion. Which for us will be the x direction. So if we go back and look at our picture, we can see, and if you were to imagine pulling the M2 out so it all points in a straight line, we have all of these forces acting in the same direction. So if we start from mass 1, we would have a negative force of friction minus m1g sine theta plus a tension, because there's that tension in that rope there. And then just following the system around, I get a minus tension and then a plus m2g. And if I'm looking at all of my forces need to be divided by all of my masses. And this is just coming from our mother equation of F equals ma. So if I'm solving for acceleration, that means I need to divide by mass. This is the same thing that I've done here. This is my x acceleration. And hey, look, these tensions cancel out. So I could rewrite this, just because I don't like having negatives in the front. I could have m2g minus the force of friction minus m1g sine theta divided by m1 plus m2 equals ax. And then plug it in, and this is the exact same equation that we had before. Alright, so I hope all of this helped you, and I can get so many more views on my YouTube channel. This will be, well, obviously, if you found it, I don't need to tell you that it's posted on the Fusion page, so that's kind of redundant. But I hope this helps, and I will see all of you on Monday or Tuesday or whenever it is I decide to see you. Alright, have a good weekend, guys. Bye.